Designing nanoparticles intended to cross the blood brain barrier. It is important to predict that the significant amount of a given nanoparticle might deliver its cargo to the brain parenchyma. Although there is no clear pattern, several characteristics of the nanoparticle itself might contribute to a successful blood brain barrier crossing, such as size, charge, and surface modifications. Now we'll discuss this one by one. First one is size. The final pathology of nanoparticle the final pathway of nanoparticle entry into the endothelial cells by transcytosis is determined by the initial step of endocytosis. Nanoparticles with a size smaller than 200 nanometer have more chances to efficiently cross the blood-brain barrier. Next property is charge. Positively charged nanoparticles can use the adsorptive transcytosis pathway more easily than their neutral or negatively charged nanoparticles or counterparts due to the negative charge of endothelial cells external membrane. On the other hand, neutral or negatively charged nanoparticles show a reduced protein adsorption leading to longer circulation times. However, longer circulation times may also be achieved by coating the nanoparticle with compounds such as PEG. So, that is polyethylene glycol. Pegylation generates a steric barrier around the nanoparticle which avoids opsonization and their subsequent elimination by the mononuclear phagocytic system. Different sweeter ionic molecules can be used which may overcome the low cell uptake efficiently observed for PEG coated nanoparticles. Another property is surface modifications. Nanoparticle surface decoration with different ligands mainly aims to increase blood brain barrier crossing by the nanoparticles by means of taking advantage of transport and receptor mediated transcytosis. In this sense, ligands for targets such as GLUT1 or albumin transporters, luciferin receptors, LRP, which is targeted by angiotensin 2, or transferrin receptors have been used. One important concept when dealing with incorporating different ligands into a nanoparticle to increase receptor mediated transcytosis is avidity. Basically, placing too many affinity ligands, which is high avidity, on the surface of a nanoparticle can hinder endocytosis by endothelial cells, which make the nanoparticle and its cargo remain attached to the endothelial cell plasma membrane. This issue can be overcome by placing fewer ligands which increase affinity for its receptors. Decorating the nanoparticle with cell penetrating peptides that avoid the endocytic pathway and deliver the nanoparticle and its cargo directly in the cell cytoplasm. Increasing nanoparticle circulation time that leads to an enhanced brain uptake using ligands such as PEG that also decreases nanoparticle opsonization and sequestering by the reticuloendothelial system.